So we have done enough theory work with the general theory of p-n junction, and today I will be describing some special purpose diodes, p-n junctions. So first is what we call Zener diode. It's Zener is name of an American scientist. So this is Zener diode, and the Zener diode is characterized by its very special reverse bias characteristics. So if you have I here and V here, so normally diodes will have a characteristics like this, and then on this side with a different scale, we have done that. All diodes do this. This is milliampere scale, this is microampere scale, so the scales are different. So in reverse bias, you have a current in that reverse direction, and the current is very small in microamperes, almost saturates, and then at certain place a breakdown occurs, and then it suddenly goes down. So this is the breakdown region. We have talked about this thing also. And one reason of breakdown, what we call avalanche breakdown. Avalanche breakdown. So that reason is that if you have a p-n junction and depletion region is there, so the electric field is there, this is p side, this is n side, the electric field is this way. So any whole electron pair which is here, and or the minority carriers which are giving rise to this reverse current, they are accelerated by this field. So if the region is wide enough and the electric field is able to impart enough energy to the charge carriers so that they collide with the atoms and break the bonds, so that new electron hole pairs are created. And once new electron hole pairs are created, they are also accelerated by this field, this electric field which is here. So electrons are accelerated towards right, holes are accelerated towards left, and they may also gain enough kinetic energy to break even more those valence band electrons, and they can made free, and this way large number of electron hole pairs may get produced if this process starts. So that is that breakdown known as avalanche breakdown. But in Zener we are using this kind of phenomena, but the breakdown is controlled. We control at what voltage this breakdown will happen, and that is very sharp, that is very sharply defined. So that is the difference. So this is the kind of characteristics, and here in a very short range it just goes down. Okay. So for Zener there is a different mechanism of breakdown, and that is called Zener breakdown. And the interesting part is that breakdown occurs at a almost sharply defined voltage. Okay, and what that voltage is, that can be controlled by putting that those diffusion, the impurities, concentrations of impurities, and so on. So normally for Zener we have high level of doping, high concentration of doping, high concentration of impurities. So Na and Nd are large, heavily doped. These are the words that you will find, heavily doped. So as a result, this depletion layer is very thin. This depletion layer is very thin, of the order of micrometers, 1 or 2 micrometers or less, like that. So if the depletion layer is very thin, and then you apply this reverse bias voltage. The depletion region is very thin and you apply this reverse bias voltage, this electric field can be very large. This electric field, this becomes very large. Right? If you apply a reverse bias voltage, if this P side is connected to negative, N side is connected, positive is connected to this N side, so it is reverse bias. So we are applying this voltage over this, and in this region, beyond depletion region, the voltage hardly varies. So this entire potential difference drops on this depletion region, and the depletion region is very, very small. So the electric field will become very high. Now high electric fields themselves can break the bonds. It's not that this high electric field will accelerate the electrons or holes and they will collide and they will create these whole electron pairs. Not necessary. If the electric field is strong enough, then that electric field itself can take this electron from valence band to conduction band, that bond can be broken and new electron hole pair can be created. So once this process starts, because of the strong electric field, electron holes are created in this region, and the moment they are created, remember this electric field is there to sweep them and give rise to that current. So that you can have current in the reverse bias which can be very large, because a lot of electron hole pairs are continuously being produced, and then the electric field here is sweeping them. So the electrons are going opposite to this, holes are going in the direction of electric field, and so the current goes in the conventional direction, the current goes, and that current can be very, very high. But that potential difference across this diode, across this, remains fixed, almost fixed. So that is the kind of so you will have to put a resistance somewhere, so that the extra voltage drops here. Okay, here the voltage drop is just, if it is made for 2 volts, it's 2 volts, right? The moment it becomes 2 volts, you have all this process starting, and then it cannot increase beyond 2 volts, because at 2 volts itself you try to increase and the current will increase very high, and if you put really more than that 2 volts, then the whole thing can get burnt, right? So you must put a resistor here, so that any extra voltage that drops here and here remains the voltage for which it is created. Normally by adjusting this NA, ND and width of the depletion region, etc., you can make this for say 2 volts to some 100 volts or so, anything you like. You want a Zener which should break down at 18 volts, yes, one can create that. A Zener which breaks down at 8 volts, yes, you can do that. 24 volts, yes, you can do that. 100 volts, yes, you can do that. So it is under control. So this is the kind of situation for Zener diode. Your reverse, it is always operated in reverse, and we will talk about the use of this, application of this, and it's always in reverse bias condition, and this is explored, that at a very sharply defined voltage, the current will be there and you cannot increase the voltage further in reverse direction. Okay, the current will keep on increasing, but this voltage will remain fixed. So that's the kind of diode we have. There is a symbol for that, separate symbol. Our usual diode, when we write, we draw a triangle and then we put a line here, a line here, a line here. So this denotes your P side, this denotes your N side, and if the current goes in this direction, that is the forward biased current. If the current goes in this direction, that is the reverse bias current. Okay. But for Zener diode, you have this symbol has slight modification. You put 2 more lines like this, like this. So this is a symbol for PN junction. So this Zener diode. So wherever you see this kind of a symbol, these two extra lines, you understand that we are talking of Zener diode. So now let us see how this feature can be utilized for some useful purpose. So let us make a voltage regulator. When we use a power supply to get some DC voltage, the power supply is supposed to give me the DC voltage at one particular fixed voltage as a function of time. So that's good DC. But normally it doesn't happen like that. If you have a power supply, DC power supply, like our adapter, okay, the chargers which we use with our mobiles or with our cameras or with our laptops, that charger is nothing but a power supply. We put it in that 220 volt socket, and then on the lead what appears is a DC of some 3.2 volts or whatever is that appliance needs. Okay. So this power supply, this DC power supply, supposed to give me voltage difference here must be fixed as a function of time. But many times it doesn't happen like that. There are some fluctuations. And if there are some fluctuations, my appliance may or may not accept that. It may be very sensitive. So that if it needs 5 volts, it needs 5 volts. It should not be 5.1 or 4.9. So that regulation, that stabilization can be done with Zener. Suppose I have some equipment which needs, my equipment needs 5.0 volt. Okay, I have some equipment which needs 5.0 volt, not less, not more. What I can do? I can create a circuit. I can take this power supply here, and then and suppose this is this gives me a 10 volts. Suppose this is a 10 volt power supply. So it is supposed to give me 10 volts. It is supposed to give me this kind of waveform as a function of time, but what it is doing, it's giving this kind of thing. So it is fluctuating from 10 to, let's say, 10.2 here, 9.7 here. It's fluctuating. This kind of supply is coming here, and then we have some equipment here. Let us say this is some equipment. Let me denote by some resistance like symbol. Suppose this is the equipment, and here I need just 5.0 volt. So I'll take a Zener diode whose breakdown voltage is 5.0 volt, and then I'll connect it here. Let us say I connect it to a resistance normally called shunt resistance, and then this is the diode here, and that is in reverse bias. So this is the circuit I make here, and here I take my supply from. So let me call this RL, load resistance. Suppose this is just a resistance, a load resistance. Okay, whatever equipment is here is equivalent to a resistance, and it is this. And this Zener diode which I am using, for that the specification is that the breakdown voltage is 5.0 volts. And there is one more specification which is very important. This you cannot supply a huge current into any diode. It will just thermal heat generation and it will burn. So there is a power rating. There is a power rating, and power rating means maximum power that can be given to this Zener diode. So suppose this power rating here is 0.5 watts. So that means in the Zener, when you are sending current, okay, this is I and this is V, this is reverse bias. So the current can be this much, the current can be this much, the current can be this much at the same, almost same voltage, current can be anything. So the voltage which is here on the diode and the current which is going into the diode or through the diode, that product V into I should not be more than this power rating. That's the meaning. If you send more current, then you run into danger of destroying the Zener. Okay, so this is another specification, that power rating. Suppose for my Zener power rating is 0.5 watt. What does that mean? That means the current, maximum current which can go through this Zener is what? V into I is power. So it should be 0.5 watt and divided by 5.0 volts. That should be the maximum current, and that means it is 0.1 ampere or 100 milliampere. So if the rating of the diode is, breakdown voltage is 5.0 volt, power rating is 0.5 watt, then you are requested not to send more than 100 milliampere current in this Zener. So that's it. So this RS, this resistance is put to ensure that the current is not 100 milliampere. To start with, let us say there is no load. Suppose there is no load. Okay, so let me break this. Suppose it's just RS and the Zener. And suppose this is 10 volts. This is 10 volts. It is giving me 10 volts. Fluctuation is there, but 10 volts here. And your circuit is just this. This is the circuit. And remember, this side is plus and this side is minus. This is DC power supply. So one side is positive, one side is negative. So this is plus and this is minus, and then it is reverse bias. Okay. So how much is the current? How much is the current? The current will be decided by this RS. So suppose this, so what should be the RS? If I drive 100 milliampere through the Zener, if I drive 100 milliampere through the Zener, that same 100 milliampere is going here also. It's just one circuit. And the voltage here, from here to here, the voltage across this Zener, remember here, this is IV characteristics. So this is the voltage. Voltage across this Zener, when it is operating in this breakdown region, right? We are somewhere here, we are operating somewhere here. So the voltage is fixed, and that is the breakdown voltage. So voltage on the Zener, that is fixed, and that is 5.0 given. That is 5.0 volt, right? Whatever be the current here, the voltage here is 5.0 volt if you are operating in that breakdown region. So what is the voltage on RS? The voltage on RS, let me write it Vs, will be 10 volts. If I take, so this is 5 volt drop here. So if I take this as 0, this will be 5 volt, and this is 10 volt. So the drop is 5 volt on this RS also. So Vs is 5.0 volts, right? 5.0 volts. Okay, this is this 10 volts and minus this 5.0 volt. That is this 5.0, or let me write it 5 in fact. Let me write it 5. What is the difference? What is the difference? Why not 5.0? Why 5? Because Zener, it is fixed 5.0. That comes from here, from this characteristic, it is fixed. But this one, this voltage, that fluctuates with this power supply. So if power supply goes to 10.1, this will go to 5.1. If power supply goes to 9.9, this will go to 4.9. So I should not write 5.0 here. Nevertheless, what is the current? What is the current through this RS? That current will be 5 volt divided by this RS. Okay, voltage drop divided by this resistance will be the current. But that same current is going through the zener, because I have already broken this part. So the same current is going through zener, and that current should not exceed 100 milliampere. So what should be this RS, so that I ensure that the current in zener is 100 milliampere or less. For 100 milliampere, if this is 100 milliampere, 0.1 ampere, if I take this as 0.1 ampere, then this is 5 volt divided by RS, and RS will be equal to what? 5 volt divided by 0.1 ampere, and that is 50 ohms. So if you put 50 ohms, it will be 100 milliampere, and if you want to keep it below 100 milliampere, this RS should be more than 50 ohms. So for a circuit, this RS, if this is the rating, if these are the ratings, then this RS should be more than 50 ohms. So now let me come back to my circuit here, my equipment here, my appliance here, and let's choose some RS. Definitely I won't like to choose just 50 ohms, so let me take it 100 ohm. Let me take it 100 ohm, and I connect this, and suppose this RL is 1 kilo ohm. Right? Now see what happens. Analyze this circuit. The voltage on this RL is 5.0 volts because it is directly connected to this zener. So this point is directly connected here, and this point directly connected here. So this 5.0 volt must appear here. So it will be there. So what is the current? What is the current in that load? IL. Here it is 5 volts. So that will be 5.0 volts, and divided by this 1 kilo ohm. So that is 5 milliampere. And the equipment will receive this voltage and this current 5 milliampere only. Okay. And now what is the current through this RS? Again, if this is 10 volts, this is 5 volts, this will be 5 volts. So what is the current here? Now IS is equal to 5 volt divided by 100 ohm. How much is this? This is 0.05 ampere, that is 50 milliamperes. And how much is the current from this zener? You have 50 milliamperes here, you have 5 milliamperes here. So here it's simple to see that current through that zener is 50 milliampere and minus 5 milliampere, and that is 45 milliampere. Right? Now suppose there is a fluctuation in this voltage, and this 10 becomes, let's say, some 10.2. This 10 becomes 10.2. What will happen? Right? So analyze it once again, taking that this 10 has become now 10.2. So what happens? Now this is 5.0 volt, no change, and therefore this is 5.0 volt, no change, and therefore the current here is 5 milliampere. Up to here everything is fine. IS, there will be change in IS. What is IS now? How much is the voltage here? This is 10.2. Out of this 5.0 is here. So what is left? It is 5.2. So now this is 5.2. Okay. And if this is 5.2, then the current IS is not 5 volt divided by this. It is 5.2 volt divided by 100. So I remove it from here. This is now 5.2 volt and divided by 100 ohms. So what happens now? It is 0.052 amperes, that is 52 milliamperes. So this current is now 52 milliamperes. Okay, and this is 5 milliamperes. This is 52 milliamperes. So how much is the current here? IZ. IZ is equal to 52 milliampere and minus 5 milliampere, and that is 47 milliampere. So you see the current through the zener has changed. In the previous case, when it was 10.0, this current was we calculated 45 milliampere. Now the voltage has fluctuated and this current has changed. From 45, this has become 47. But my equipment, my appliance, this load resistance, no effect on that. It is getting a regulated power supply, 5.05 milliampere current is going through this. So this is how a voltage regulator is made. Whatever power supply you make, and if you then connect a zener here and a shunt resistance here and then take your output from here, this is a regulated power supply. It's meant for a particular voltage and it gives that voltage. And same will be the story if the voltage goes down. Okay, from 10.2, if it goes to say 9.8, 9.7, you can make the calculations. This zener will take care of all that fluctuations and this equipment will remain the same. But remember, your fluctuation should not be so high that this voltage goes less than the breakdown voltage. Then this will not work. If it is meant for 5.0 volt and supply voltage goes to 4.8 or 4.7, then this whole thing will not work, because then you are not in the breakdown region. Then you are not in the breakdown region, you are somewhere here. Then it is not true that your current changes but voltage does not change. In fact, the current doesn't change much. Current through the zener does not change much and the voltage can change. So this has to be more than the breakdown, that's it. After that, let it fluctuate and it will give you a constant DC voltage. So this was one application, one special purpose PN junction made to follow this, and there are many others. LED is one, so and this photo detector is one, solar cell is one. So next lecture we will take one of these things or maybe two of these things.